Today we will look on how to graph systems of inequalities. In our first example, it says we want to find the solution set of the system of inequalities. So I'm going to take my first equation, x minus y is less than 1, and I'm going to solve for y. So I'm going to subtract x to both sides. So we're left with negative y is less than 1 minus x. Remember with inequalities, when we divide by a negative, we have to flip the inequality sign. That means the less than sign will become a greater than sign. So the equation we will actually, or inequality we will actually graph is y is greater than negative 1 plus x. Note the y-intercept is negative 1, and our slope is positive 1. Remember, I want to see a minimum of 3 points. And remember, because it's a greater than sign, we're going to dash our line in. If I were to take 0, 0 and plug it into the original equation, is 0 less than 1? Yes. So that means we draw arrows above because I want it pointed towards my test point. If I were to go into the second equation and solve for y, so 2x plus 3y is greater than or equal to 12, we're going to subtract the 2x first. So 3y is greater than or equal to 12 minus 2x. Next, we'll divide by 3. So we have y is greater than or equal to 4 minus 2 over 3x. This time our y-intercept is 0, 4. So we go up to 0, 4 on the y and put a dot. Slope is negative 2 over 3. So I will fall 2 and go right 3. And sometimes I like to do this until I fill up my graph, just so it looks nice and pretty. And this time, because I have a greater than or equal to, we will draw a solid line. Now, if we were to take 0, 0 and plug it into our original inequality, is 0 greater than or equal to 12? The answer is no. So we shade the opposite area of our test point 0, 0. So now, where all the arrows point is where we shade. So this is how we graph a system of inequalities. Notice it is graphed. We have our dashed line for x minus y is less than 1. We have the solid pink line for 2x plus 3y is greater than or equal to 12. And notice the combined shaded region is our solution set. Now take a minute or two and try the example you try. Here is your result for the example you try. Notice the top equation, when you solve for y, you have 2y is less than or equal to x minus 4. So when you divide by 2, you have y is less than or equal to 1 over 2x minus 2. Okay, so our y-intercept is positive 2, slope is positive 1. Oh, I forgot my negative sign, no wonder. Okay. So we're going to go down 1 and right 2, put some dots. Up 1 and left. And because it's less than or equal to, it is a solid dot. The pink line is already in slope-intercept form. So notice we have a y-intercept of -1, slope is -1, so I can go up and left. Solid line, if I do 0, 0, 0 is greater than or equal to -1. So arrows point this way. Forgot to do our test point for the other point. 0 is greater than or equal to 4 if we were using 0, 0. And you can see our combined shaded region. In our next example, we are doing the same thing. If I were to take this first inequality and solve for y, we have y is greater than 4 minus x. Notice this time our y-intercept is the point 0,4. Our slope is down 1 and to the right 1. Or up 1 and left 1. Points are not going in the right place. And we will use a dashed line because it is greater than. If we were to test 0, 0, is 0 plus 0 greater than 4? No. So our arrows point away from our test point 0, 0, and they point away. If we look at the bottom line, we are just going to subtract x to the other side. Y is less than -1 minus x. Our y-intercept is 0, -1. And slope is also down 1 and right 1. Okay. And we'll use a dashed line again. Okay. If we were to plug 0, 0 into the original, 0 plus 0, is that less than -1? No. So our arrows point away from 0, 0. Remember our y-intercept is 0, -1. If I had pretty graph paper, our graph would look much better. Notice that we don't have a solution set that overlaps, so this would be an example of that. Here we can see our top example. This time it is clear what it should look like. Note the first equation, remember we said had a y-intercept of 0, 4, slope of -1, the arrows pointed up and away from our test point 0, 0. Whereas our other E line had a y-intercept of -1 with a slope of -1 and the arrows were pointing away. There is no overlap shaded region, so this is technically a no solution graph. Okay. So let's move on to the next problem. And again, we're doing the same set of graphing. If I want to graph x plus y is greater than or less than 8, remember we're going to subtract the 8 first. Or not the 8, the x. Because this is in slope-intercept form, this is my y-intercept, 8, 0, 8. So we go up to 0, 8 and we put a dot. Looks like so. And slope is down 1 and to the right 1. Let me see if I can. Okay, so we said 0, 8. Slope is down 1 and right 1. Now, if we look at our inequality, it is just a less than. So if it's just less than, we will use a dashed graph. And if we use 0, 0 as our test point, Is 0 plus 0 less than 8? Yes. So that means our arrows face our test point, 0, 0. Our next line in our system is x is greater than or equal to 0, which is already in slope-intercept form. It is actually a vertical line that is solid along the y-axis. Where are my x values larger than 0? That would be to the right. So my arrows go to the right. And then the third equation, y is greater than 0. That would be my x-axis. I need to go this way. Now, if I want where y is greater than 0, my arrows are going above, because all of my y values larger are like 5 and 10. I don't want the negatives. Now, the area in which all of our arrows point to is this triangle here. And there's our solution set. Okay, remember when we graph absolute values, the first thing we're going to do is we're going to box our parent function. We're going to graph y is the absolute value of x. Remember, this -1 inside with x means this it has a right shift, so we're going to go right 1. And this one that's hanging out by itself, we're going to go up. So all of the green dots we just graphed, we're going to move right 1 and up 1. And because it is less than or greater than, we're going to dash. If we were to test 0, 0, notice we have 0 is greater than the absolute value of 0 minus 1 plus 1. 0 minus 1 is -1. Now we have 0 is greater than 1 plus 1. Is 0 bigger than 2? The answer to that is no. So my arrows face the opposite way of our test point 0, 0. If we were to draw a box around our parent function for y is less than or equal to negative the absolute value of x minus 3 plus 6, we're going to graph the negative absolute value of x. Remember, if it's negative in front of the absolute value, it opens upside down. Now we're going to shift all of the blue dots right 3 and up 6. And because it's less than or equal to, we will draw a solid absolute value graph. Now, if we were to test 0, 0 here, notice we have 0 is less than or equal to negative 3, because 0 minus 3 is negative 3, absolute value. And we get 0 is less than or equal to 3. And that is a true statement. So our arrows face towards our test point 0, 0. Now the region in which all of our arrows point to is our solution set. So it's this little area in between our two absolute values. Notice here is our solution. Same picture as before, it's just crisper. So this is what your graph should look like. And this concludes our systems of inequalities.